Okay, so recall we started talking about the tangent space and the normal space. So before that, we first consider the concept of curves. So suppose we have a curve defined as a function from an interval on the real line to n-dimensional space. So you know that geometrically that means we have a curve in some kind of space, right? For example, if it's 2D, then it will be a curve like this. In 3D, you can also imagine a curve. You could even have a curve like this in 2D or 3D or even in high-dimensional space. But what actually curve is described is described by a mapping from the set of real numbers where you have this A and B, and this is the domain for the mapping, and this interval is mapped into, say for example in 3D case, mapped into a curve like that, or maybe just a simple curve like this. So this AB will be mapped to from here to here, and when we said that the variable is t, the t goes from A to B, then you go from here to here in this direction. All right, and this mapping is called X, and we use X. Vector X means that it is a mapping from a scalar t to a point in the n-dimensional space. In this case, it's a 3-dimensional space. So this X can be considered as a mapping from R to R3, or more specifically, it's a interval on the set of real numbers R. Okay, and it maps this. It takes this t to X of t, okay, which is the dimension, which is the vector in the 3-dimensional space. But in general, it could be n-dimensional space. Okay, that's the X. And the derivative of X, we said that the derivative of X is just this X itself maps this t to a vector, say x1 of t, all the way to, say, let's consider the most general case, where we have n here, that's x1 of t and xn of t. And this x1 through xn, they are the coordinate of the point. So for example, at this point, when t is some number, then this will project this to the three coordinates. This is x1, this is x2, this is x3. So this value here will be the x1 of t, this will be x2 of t, this will be x3 of t. Okay, and so we have a n-dimensional vector here, and each one of them is a scalar valued function. Okay, so you can consider each one of them just like a univariate function and takes and maps a scalar to a scalar. So we can consider the standard derivative. That is the meaning of this x prime. So it's take the derivative of this function, and then it's essentially taking the derivative of each of these components. So that's the first order derivative, or just we call it derivative. And beyond that, we can also consider the second order derivative, which means that we take the derivative twice for each of the points. Okay, and that becomes this one. So again, it is an n-dimensional vector. You just that each of the components we had taken the derivative twice. Okay, so now we introduce the concept of tangent space. So the tangent space can be interpreted in this way. The tangent space of a certain, for example, you know that in 2D case, when you have, say, a curve, then the tangent space means that for example, this point, you have a tangent line, right? And this line is perpendicular, is parallel to this line here. So the line I draw below here, this is called the tangent space of the point, of this point, which we call it, for example, this is the x, this is the h of x. So at this point, this is the x, hx. Okay, and this line here is the tangent space. All right. In 3-dimensional case, if you have a line, for example, you have a curve here, then, for example, you're looking at the point here, then this will be the point x, hx. And the tangent line means that again, it's just that there's a tangent line here, and then you just always just move it to the origin. So you could be a line here. This will be the tangent space, right? So in general, what is defined mathematically is that if you have a constraint set, omega like this, and it's specified by this constraint here, then the tangent line of a point x in this space is called, is defined in this way. So geometrically, what that means is, for example, we consider the case where n is equal to 3, and this omega of this, imagine that if we have just one constraint, meaning that this h just has h1 of x equals to 0, then this will give us, specify a surface. If we have two of them, we have h1 and h2 in this h, then we have two surfaces, and we want both of them. If we take the intersection of them, this omega is essentially the intersection of the two surfaces. Then we'll get just a curve. Okay, so when n equals to 3, then this will specify either a curve or either a surface or a curve, or even you have more than two. Say you have 3 of these constraints inside here, then we could end up just with one single point. Then in that case, the omega will be just a single point. Okay, so for example, let's consider the case where the h has only one constraint. That means this h is a scalar value. This 0 is just a scalar 0. In this case, omega usually specify a surface in 3-dimensional space. And what a surface looks like, say again, this is 3-dimensional space. Surface may look like this, right? So this is omega. And at this point x star, we will have a tangent plane just like that. Okay, and this tangent plane will be shifted to the origin because you don't really care about where it's located. You just see where what is the norm and what is the orientation of this plane. So we'll be shifted to here, and this plane here is called the tangent space. It calls the t x star. Okay, so this point itself is x star, and you have this omega, which is where this omega star is a point on the omega. Then the tangent space of the surface omega at this point x star is just like this tangent plane here, and but you shift it back to the origin. Okay, mathematically it is defined in this way. The tangent space at point x star is equal to all the vectors y such that the dh times y is equal to 0. Okay, so recall what is dh. dh is the Jacobian of h, right? The dh of x is equal to h is a mapping from Rn to Rm. Okay, then dh is a matrix, is a Jacobian matrix of size m by n. So it has m rows and columns. And recall what it is. The h itself, it is h1, or I write it more specifically, the hx, it takes every vector x into a m-dimensional vector, and the m components of this m-dimensional vector is h1 of x all the way to hm of x. Each one of them is a scalar valued function. Okay, takes a vector and maps it to a scalar. And then the Jacobian above is the gradient for each of these functions. But we put the gradient as rows, and then put it as the rows in this Jacobi matrix. So this will be gradient h1 of x And we put it transpose means that originally it's a column vector, but I want it to be a row vector. This row vector takes the first row, and then all the way to the last vector, which is a gradient of xm, and again it takes a row. Okay, so this one is a m by n matrix. This is the Jacobi matrix. So here, this m by n, and this y is a m-dimensional vectors, n by 1. Okay, so this tangent space is essentially just all the vectors y, such that we multiply this Jacobi matrix to y, you get 0. Right? And this is essentially just saying that y is just in the null space of this Jacobian. Okay, remember the null space of a matrix A. Null space of the matrix A is all the vectors y such that ay equals to 0. Now this Jacobi takes the row of this A, and the y is the vector in the null space. So this tangent space is essentially just the null space of this Jacobi matrix. Okay, that's what we're trying to say here. This n means the null space. Okay, so remember that when the x star is a regular point, then the Jacobian matrix has a full rank. But since we already have the m less than or equal to n, so the rank of a matrix can be as large as the smaller value of the m and n. So the rank of this Jacobian will be equal to m. Okay, and in this case, the null space is equal to n minus m. Right? The reason is because this dh is a Jacobian is m by n matrix. This is the m by m rows and columns. So you can imagine that I have m of these rows right here. And these rows together can form a basis, but this basis will not be complete because this is each one of them is an n-dimensional vector. So they form a basis, incomplete basis in dimensional space. And because the rank here is m, so that means that those m rows here are linear independent. So I can use them as m linear independent vectors in Rn, but they're not complete. These m rows together can form a m-dimensional subspace in the n-dimensional Euclidean space. And there is another space that is perpendicular to this subspace, and that space will span the rest of those spaces. So imagine that if you want to complete these m linear independent vectors, you complete them into a set of n complete bases. Then you will need another n minus m bases, and those n minus m bases will be in the null space because they will be perpendicular. Each vector in that null space will be perpendicular to arrow one here, arrow row here. So that's why the null space of this matrix here will have a dimension n minus m. Okay, that's the number of new basis vectors you need to complete a set of n bases, and you already have m of them here. But the other n minus m of them will be perpendicular to this, and they will be that's why they will, for any one of them, we will multiply this matrix to this vector, you just get 0. Okay, and that's why those n minus m basis vectors will be perpendicular to this, and anything spanned by those n minus m bases will be perpendicular to these rows as well. Right? This is something you know in linear algebra. So the dimension, since we showed that the tangent space is nothing but just the null space of the Jacobi matrix, so the dimension of the tangent space will be equal to the dimension of the null space. And as we said, if there are m rows in the SH, the H is a mapping from Rn to Rm, and this point x star is regular. That means the Jacobi matrix has the rank m. Then the null space of this Jacobian will have a dimension n minus m. Okay. And that is corresponding to the case here. Remember that right now we have a surface in a three-dimensional space, and we only use the one constraint. So in this case, n equals to 3, it's a 3-dimensional space. M equals to 1 because we only have one constraint. And this one constraint will specify a surface in general. And this surface, and now you consider the tangent plane, which is this, or you want to move it here, it will be this. And apparently the tangent space here has a dimension 2, right? Because it's a plane. And that is exactly equal to this 3 minus 1, which is 2. If you have two constraints, this H has H1 and H2, then you have two surfaces. And then the H will actually specify a curve, which is the intersection of the two surfaces. In this case, n equals to 3, but m equals to 2. And then we will have a curve. And then this curve will specify a tangent. Will specify a tangent line. Because imagine you have a curve here, then you have a tangent line. And this tangent line is corresponding to the tangent space there. And in this case, the dimension of this tangent space should be equal to n minus m, which is 3 minus 2, and that is equal to 1. And that is the dimension of this line, which is the tangent space right now. Okay, so this tells you what is the dimension of the tangent space, and that's just a direct calculation from the dimension of the null space. Okay, so and below I read that sometimes we write the tangent space as a plane tangent to the omega at the point x star, and in this case we just shifted the tangent space to that point that is actually tangent to the omega geometrically. So in this case, this is the t of x star, and this is the tp of x star, okay, which is just shifted by this x star. Okay? But essentially they have contained the same information. Okay, and later on we're going to use just the tangent space. Okay, now let's consider an example. Suppose we have this omega specified in R3. So omega will be in R3, and it specifies two constraints, this and then this. Okay, remember that one of them, for each one of them, you will specify a surface, and two of them will specify two surfaces, and together these two will just take the intersection of the two surfaces, and then we're supposed to get a curve. And so this omega should be some curve in three-dimensional space. But this curve is just a straight line. The reason is the first one tells us that x1 has to be equal to 0. So imagine that you have this three-dimensional space, x1, x2, x3. And x1 equals 0 means that this we must be living on the x2, x3 plane. And the second one tells us that an x1 is equal to x2. Okay, x1 is equal to x2. So in this case, the x1 is 0, x2 is 0. So we can only live on the space of the dimension of x3. In other words, this first constraint here tells us that we're living on this, or the plane specified by this x2 and x3, and this one here specifies that all the points that such that x1 is equal to x2, and this will be this plane here. Okay, and it can be this is infinitely large, but I'm just drawing this picture here. So imagine that you have this surface, which is like a hyperplane or plane in the three-dimensional space, and originally you have the first of each one gives you this plane, which is also a plane infinitely large. You take the intersection of these two, then you just have this single line here. So this is what this omega actually is. It's just this line. Okay, and then so that's what omega actually is. But now let's look at what's the tangent space. First, to compute the tangent space, we first need to calculate the Jacobi matrix. The Jacobian of H is just, as we said, just the gradient of H1 and then gradient of H2 and put as two rows. The gradient of H1 is just the gradient of this, okay, gradient of this. So it's partial derivative of this with respect to x1, x2, and x3. And apparently that gives us 1, 0, and 0. Right? So that's this first row here. And then we look at the second h2. So h2 will take the partial derivative with respect to x1, x2, and x3. We'll get 1, -1, so 1 from here. And the derivative with respect to x2 will get -1 from here. And then there is no x3, so the partial derivative will be 0. That gives us the second row here. So this is the tangent, this is the Jacobian matrix. And apparently it doesn't depend on x, which is quite special for this problem. But in general, it should be dependent on this x. Okay? But here is just due to the special choices of x1, h1, h2, it doesn't depend on x. But no matter what, we can always compute the tangent space. Since this doesn't change for any different point x, so the tangent space will be also the same for every x. The tangent space, according to the definition we had earlier, should be the null space of this matrix. And the null space of this matrix is all the vectors such that when you multiply by this matrix gives us 0. Okay, so imagine that you have this y here, and you need to multiply this to y, you get 0. And then what kind of y? The set of these vectors y will be your choices. Okay, and apparently in this case, if you have this y here as the y1, y2, and y3, you want this to be equal, you multiply this matrix to this vector, you get 0, then apparently y1 has to be equal to 0. And the second row tells that the y1 equals to y2, so y2 must be 0 as well. But y3, it doesn't matter what it is. No matter what the value y3 is, this vector y will always give you this 0. We multiply this matrix to y, you always get 0. Okay, so that means the tangent space in this case is this. Okay, is all the vectors with the first two components 0, the last component arbitrary. And that is exactly this line here, because the omega is this, and the tangent line, since it's a straight line here, the tangent line is the same line here, right? It's just the same as the original omega, and that is specified by this. Okay, that so happens for every point in this omega. So for every point, that means for each point on this line, the tangent space is just this line itself. Okay. All right. So now we give you a important result that we're going to use later. We should actually from calculus or geometry, probably calculus. So what it says is, suppose we have x star, which is a regular point. By that we mean, again, the Jacobian, if you like, always write the vector notation. The Jacobian of h at point x star has a full row rank. Okay, full row rank. So the rank of this equals to m, the number of components in h. And then the y is in the tangent space of x star if and only if there exists a curve. You can define a curve that is mapping from this interval to omega such that at the point t equals 0, so t can be taken, can be any number from this interval. When t equals to 0, it reaches to the point x star, and the derivative at that point, which is the derivative of the curve at that point, is equal to y. So what this means is, again, let's use the picture before. Just imagine that I have this surface right here, and then this point is the x star. So this is the omega. This point on the omega is the x star, and let's say that this is the tangent plane, and we have a vector in this tangent plane. So I just draw the vector here, but originally maybe the space like this, but it doesn't matter. I just need the dimension, the vector itself. So say I have this vector, which is the y. Okay, so that means this y is a vector in the tangent space. I can move this plane and this y to shift it to the origin, but it doesn't really matter. I can move them here. and then there's a y here. But you know, I draw this, then it's pretty clear what that means. And then the y is in the tangent space if and only if there is a curve. So you can find a curve that is mapping from negative delta to positive delta 0 here. You just map from this interval to this curve right here. So this curve, what I'm drawing, here is on this plane, on this surface omega, and it is just it's just a mapping from this interval on the real line to this curve on this omega, such that when the t goes from negative delta to positive delta, it will pass through this origin 0. And when you move from here to here at t equals 0, you reach the point x star. At the same time, the tangent line, the derivative of this, or the derivative of this x at this point 0 is equal to this y here. Okay, is exactly this y here. So this is what this theorem says. So the y is a point in the tangent space if and only if you can find a curve x such that this, when t equals to 0, here, the x0 is just x star, and the derivative of x at t equals 0 is equal to y. Okay, so that is the theorem here. So now we prove this. Okay, the sufficiency is easy. Suppose that this part is true. Suppose there exists a curve x such that this are true. Then in this case, because it's x, it's a mapping from this interval to omega. So the x of t, for every t between negative delta and delta, this x of t will be a point on omega. So this x of t is a point on omega, and omega is specified by the set of points where h of x is equal to 0. So that means if I have this curve x of t, then the h of xt should be equal to 0. Okay, all these are vectors. Okay, or supposed to be vector. But in this case, h is just scalar because they one have one constraint in this picture. But anyway, generally this should be the case. So the h of x of t is equal to 0 for all different choices of t. So that means I map this interval negative delta to delta to some point in omega, and then further map this to Rm. So this is in Rn, and this is by x, and this part is by h. Okay, and together this is the hx, okay, of t, or this is just h of x of t. Okay, and we know that since this is in the space omega, this should be equal to 0. H of this point should be equal to 0. Okay, now this is the hx together. It's a mapping from here to here. So I can take a derivative with respect to t. Okay, when I do that, I will have, first of all, this is mapping from R1 to Rm. So the derivative of this should be dimension of m times 1. Okay, should be a scalar, should be a vector in m-dimensional space. And when we really do the derivative with respect to t, as you can see, we have to use the chain rule. So the chain rule will be applied to the outside h, which gives us this, and then the inside, which is this. Okay, so when we take the derivative, okay, we take the derivative of this h x t. With respect to t, we're supposed to use the chain rule, which is d of h at xt. So this is the Jacobian of h at the point xt. So this part should be m by n. And then we need to take the derivative of the inside, that is x prime t. And we know that this is a curve, and take the derivative, which is the derivative, which is n by 1. So together, we should get m by 1 vector. And when we evaluate this at 0, so when we evaluate as t equals to 0, we'll get just the Jacobian of x of h at x0 times the derivative of x at 0. But remember that this curve, it reached the point x star when t equals 0, and the derivative there is y. So that means this is x star, and this is y. So this is essentially just giving us dh of x star times the y. Okay, and because of y is in because this came from a constant function, but h of hx together is the mapping from t to Rn, but it's a constant 0. So that means you take a derivative, it should be 0 as well. So the derivative of this must be equal to 0, right? And now we linked the this and this, it should be equal to 0, and this tells us that the y is in the null space of the Jacobi matrix, the Jacobian of h at x star, and that means y is in the tangent space. Okay, it's in the tangent space. Okay, now let's move on to the other direction. The other direction tells that we want to show that if y is in the tangent space, we want to show that there exists a curve x such that x0 equals to x star and the derivative of x at 0 is equal to y. Okay, to show that, let's first consider, try to determine this function u, which is a curve, and this function u is determined in this way. It's a function of t, so the u itself, say, it's a mapping from R to, or in other words, is from negative delta, which is a subset of R, to Rn. Okay, and we want to know how this is specified. So that means I need to know for each value t in this interval, and I need to know what is the point or what is the vector here. And this one is determined by this function of t and u. Let's say that for every t and u, for every t and a vector u is the n-dimensional vector, I define this function of t and u as this. H is the constraint function that we had earlier, and it's for every fixed t and u is going to evaluate the value of this is taken as the value of h at x star, which is the given point. The y is the vector in the tangent space, as we said here. So the x star is the y are given, and then they put t here, and this is Jacobian of h at x star, and this u. So apparently this is the function of t and u only, because x star and y are fixed. H is given. So everything is fixed except this t and u. So I'm going to decide what this u needs to be, such that for any different t, I'm going to choose a specific u such that this is always equal to 0. Okay, and this also, I want this to be, I want this point to be just x star itself when t is equal to 0. Okay, and when t equals 0, apparently this is gone. And I want this whole thing to be equal to x star. That means I want this thing to be equal to 0. But remember that this x star is a regular point. That means the Jacobi matrix here has a full row rank. And when I take the transpose, it means that it's a matrix of full column rank. So I have this d h x star, and this is the matrix we said is m by n. So let's just draw it in a dramatic ways, m rows and columns. So the dh x star transpose will be a matrix of dimension n by m, right? Should be something like this. It has n rows and m columns. So these are the columns. But we know that these columns are linearly independent because this matrix has full row rank. So if I want to find some vector u, when we multiply u by this matrix, I get the 0 vector. The only choice I can have is u will equal to 0, right? Because you have a full column rank matrix. When you multiply by this vector here, m-dimensional vector here means that you're taking a linear combination of those columns, but those columns, and you want this result to be 0. It's a 0 vector here. Because these columns are linear independent, so the only choice for this vector is that everyone is equal to 0. So in this case, u will be just equal to 0. All right. So as we said at the beginning, our goal here is to first specify this function u of t. So now at least we know that when t equals to 0, the u should be equal to 0. All right. Another thing that we need to know is that can we really specify this function u as a function of t in the neighborhood of t equals to 0. Okay, and to reach that, we need to use the implicit function theorem from calculus. So if since we have this function h bar of t and u, then we will take a derivative with respect to u, and we see that if the result is a I think in implicit function theorem, the t and the u, you start with the simple case where t and u are both scalars, and this h of t and u is a scalar value function. That means it maps the t and the u to a scalar. Then we will take the derivative of h bar with respect to u. You get a derivative which is scalar, and check if that scalar is equal to 0 or not. If it's not equal to 0, then that means you can this one equals to 0 implicitly specify a function u of t. And that is the situation here. The only difference is that u right now is a vector. So remember that this h bar is a mapping from this r times rm to rm. So this is like you take the t and you take the u vector, and it will be mapped to this h bar. It should be h bar here. This is what my h bar is doing. Okay, so this h bar is of t and the u is in Rm, as we said. So when we take the partial derivative of h bar with respect to u, we'll get a t is fixed right now. Just imagine that t is fixed. So for fixed t, the Jacobian of h bar with respect to u, so I specify it with respect to u, it should be a matrix of size m by m. As long as this matrix is non-degenerate, or is non-singular, or is invertible, then we know by implicit function theorem, this will specify this. So what I'm trying to say is that if h bar of tu is equal to 0, and that the du h bar at tu is a invertible or degenerate, non-degenerate, or non-singular invertible, then this u, this h bar equals to 0 implicitly determines a function u of t. The u is a function of t to u part of t, such that the h bar of t u hat ut is equal to 0. Okay, so that's the implicit function theorem. So what we need to do is just to check if the Jacobian of this h that I determined here or specify here has a non-degenerate Jacobian. Okay, if the Jacobian of this one that I specify here has is a non-degenerate at t equals to 0. Okay, now let's see if that's the case. Then when we take the Jacobian of this h bar with respect to u, let's see what we will get. So this is my ht of u, right? So when I take the Jacobian with respect to u, the t is considered as a fixed number of t and u. Let's just treat t as a constant. So essentially it's just taking the Jacobian with respect to u of h x star plus ty plus dh x star transpose u. Okay, I want to take a derivative with respect to u. So what I should get here by chain rule is equal to dh of whatever I have inside. Then I need to take the derivative with respect to u inside. But apparently inside, this is the constant multiplied to u. So what I have here is just the d of h x star transpose, right? And then since I want to see what is the behavior when the t equal to 0, so I can specify the function u of t near t equals 0. Then when t equals 0, I just plug in t equals 0. I will have on the right hand side, this will be h of, well, we know that when t equals 0, this should be just x star of transpose, right? Because the rest should be just equal to 0, because ut at t equals 0 is equal to 0 as well. So we'll have this. Oh, sorry, there's no transpose in the first one, just this. Okay, so what this one is, it's just a Jacobian times its own transpose. Okay, the question is if this one is a non-degenerate matrix, if the product of these two is a non-degenerate matrix. And the answer is yes, because this one has a full row rank. So it has m rows and columns here, and the m columns and rows here, but it's just transpose of itself. So when we have a full row rank matrix, for example, have A has full row rank, rank of A is equal to m, then the A transpose is actually positive definite, right? The reason is if you want to check if it's positive definite, you just need to check if I multiply a non-zero x on both sides, will I get a positive number? In the apparently when you multiply x on both sides, then you will have x transpose A transpose x. Right? This is what happens when you multiply x to both sides. Then we're supposed to get a scalar. This is m by m matrix because A is m by n, A transpose is m by m. So it's m by m matrix. And then when I multiply a non-zero m-dimensional vector x on two sides, you have a row vector, I have a matrix m by m matrix, and an m-dimensional column vector here. And we'll get, apparently this is just A transpose x transpose times A transpose x. So it's the same vector, but it's the row version times the column version. And that's just the inner product of the vector with itself, and that's just the A transpose x squared. And let's see, this must be greater than or equal to 0. So that means A transpose here must be non-negative definite. But also, if x is non-zero, then this A transpose x will be non-zero as well. It's the same reason as before, because this A transpose is like this. This A transpose, and all those columns are linearly independent. And if x is non-zero, then you make a non-zero linear combination of these linear independent vectors, we will get a non-zero vector. And non-zero vector has a norm greater than 0. So here is not just greater than or equal to 0, but it's actually greater than 0. Okay, and that means the A transpose. That means when you multiply x to the two sides of A transpose, you get a positive number. As long as x is non-zero, then that means A transpose is positive definite. And that means this one is positive definite, and definitely that means it's invertible. Okay, and it's invertible, then by implicit function theorem, we know that we can decide or we can determine a function u uniquely near the t equals to 0. That means this on 0, this is negative delta, this is delta. this is the word t lives on, they will be mapped to this ut, like this, ut, and when t equals to 0, this is just x star. When the derivative at this point will be, the u of 0 will be just 0, and u prime at t equals to 0 will be non-zero. So we can decide this u. We'll decide this u of we'll define this curve u of t, and then with this u of t, we're going to set up this curve that we're looking for. We're trying to get this curve right here, and we'll specify this curve we're looking for as x star. It's just inside here, just x star ty plus this of t, because we specified this such a u of t exists. The property of this u of t is that when we evaluate h at this point, for any t near the neighborhood 0, this will be equal to 0. That means x of t is a curve on omega. And when t equals to 0, this inside will be just x star. So x of 0 will be just the x star. And also the derivative of x, we take the derivative on both sides with respect to t, then we'll have this as x prime of t equals to, on the right hand side, and we'll take the derivative with respect to t, will be just the y plus dh x star transpose u prime at t. But we know that this one is equal to just a, when t equals to 0, this is just equal to y itself. So that is the claimed right hand side here. Okay, so that's the necessity of this theorem. Okay, so now we introduce the concept of normal space. The normal space of omega is just the one that perpendicular to the tangent space. For example, again, we have this omega, we have this point x star, and then we have this tangent plane, and this plane will be x star, t of x star, or x star plus t of x star. You shift it from the origin. But it doesn't matter, as I said, this, and then this is normal space. It's just like the orthogonal completion of this tangent space. So this will be n of x star. Okay, so it's just all the vectors. It's just all the vectors that can be written as this. All the vector x that can be written as this, or you can see that this is essentially just the range of this matrix. Okay, it's the range of this matrix. So what this matrix originally is, again, the dh is a Jacobian, right? The dh is a Jacobian matrix. So the dh x star is this. So originally you have this m linearly independent rows. Now when we take the transpose, it becomes m linearly independent columns. And in this case, as you can see, because they are linearly independent, the range of this matrix is essentially just the column space of this matrix. Means that all the vectors that can be spanned by these columns right here. Okay, so this or this x equals to that means that x is in the column space of this matrix, or this whole thing here is nothing but just the column space of this matrix. Okay, and that is just the row space of this matrix. Okay, by column space we mean that the space of the space that can be spanned by this n columns, this m columns, and the row space here means that the subspace in Rn that are spanned by this n-dimensional vectors. Okay, so that's the normal space. So normal space, as we said, is equal to the column space of this matrix, and is equal to the row space of the Jacobian, and that's essentially just the span of all the rows in the Jacobian. So this is the first row up to the last row. So this is a subspace in Rn. Okay, just like this one is also a subspace in Rn, but their property is that these two subspaces are orthogonal completion to each other. Okay, so if the dimension, since we know that dimension of this is equal to n minus m, so the dimension of n normal space will be equal to just m. So the dimension of the normal space is equal to the dimension of the row space of this, because these two are the same, and the row space of this as well as has a full row rank, so that means the row space has a dimension m. Okay, so that's the dimension of the normal space. And as I just mentioned, the because this tangent space T of x star and the normal space n of x star, they form a orthogonal completion of each other, and that means the Rn can be decomposed in an orthogonal way into these two spaces. It's just like if you have a two-dimensional space, you can decompose it into a vector in R1, in x1, x2 plane, and then another one in x3. Okay, so in this case, it's like this is the T, the tangent space, and then this is normal space. Okay, and any vector can be decomposed into two parts. One part is in this, one part is in this. Okay, so that's what I said below. For any vector in Rn, you can find a pair of vectors. Y is in this tangent space, and W is in this normal space, such that V equals to Y plus W. And this is a unique way. For any vector, there's a unique decomposition of the vector into two, and one of them is in T, the other one is in N. Okay, now let's go back to the the optimization part. So with the geometry we said earlier, say now we're considering the minimization of a function f over this feasible set specified by this equality constraint hx equals to 0. Then let's say that if we have a local minimizer of this function, what this local minimizer should satisfy. And that is the we're going to consider the first order necessary condition, as we did for the at the beginning of the this semester. Okay, let's specify what that exactly is. So now suppose x star is a local minimizer of f over omega, and then because this x is a point on here of the on omega, so h of x star must be equal to 0. And then for any vector y in the tangent space, we know by the previous theorem there exists a curve as mapping from the interval. So we use negative delta to positive delta, but to make this just generic, it doesn't have to be from negative delta to positive delta. It can be any interval, and you just need that in between this interval there's a point where x is evaluated there. You get x star, and the derivative of x evaluated there is equal to y. Okay, that's the only thing we need. So that's the for any vector y in the tangent space, there exists a curve such that xt is equal to x star and the x prime t is to y. Okay, so it's just like this is the omega, and there's a point x star, and there is a y in the tangent space which is like this. So as long as you know this, we know there exists a curve that is living on this omega such that at this point, this is from A, B to there. It means that at this point, at some middle point t, this x of t is taking value x star, and derivative of x at t is at is equal to y. right? So that's what the theorem we had before. So now let's consider, because we have a curve on this one, which is the x of t or x of s, if you like to call it that way. So this x of s, this is the x. So for any point here as s is mapped to a point on omega, which is called x of s. And then we check the function value along this curve, just along this curve. So this curve itself, as we said, is x of s. And the function value on that is just f of x of s. Just track the function value along this curve, and we call this phi of s, which is just a function of s itself, right? And this will be a scalar. It's a univariate function because s is a scalar, and it's a scalar valued because phi of s is equal to this, which is a scalar. Okay, so that's how we define the phi of s. It's just tracking the function value along this curve, and then if x star is a minimizer, then we know that if we take the derivative, it should be equal to 0. So this will eliminate the issue of the constraint. Remember that only if we have the constraint, we cannot really consider the derivative or the gradient equals 0, because on the boundary, or due to the constraint, maybe the gradient is not. For example, if I have a function like this, and we restrict ourselves just to this interval, then at this minimum point, sorry, let me draw another way. As the AB here, this point, if we restrict our function to this between A and B, then at this point, although it's minimizer, but derivative is not 0. But right now, we don't have this issue, because the constraint has been taken over, or have been taken care of by this x, because I know that for any s, the x of s is a point in omega. So I can freely evaluate my f on this point, because this point is always on omega. Okay, always satisfy the constraint. So the phi of s is defined in this way. So the phi prime of s, according to the chain rule, is just the gradient f at this point times the derivative of x at s. But remember that at the point s equals to t, we'll have x of t will be equal to x star. X prime of t will be equal to y. Okay, so at the point t, we'll get this, and we know that since y is in the tangent space of at x star, so that means y. Because the x star is a local minimum, so along the curve. This point is a local minimum. So along the curve, the derivative should be equal to 0. The function value should take a value 0 there, because it's local minimum. Okay, so that means at the point t, the phi prime of t should be equal to 0. Right? And because we specified this, we said this y can be any vector in the tangent space. That means for any y, this is equal to 0. For any y in t of x star, this is equal to 0. And that means this gradient of f at x star is perpendicular to the tangent space. Okay, it's perpendicular to the tangent space means that it's in the orthogonal completion of this tangent space, which is the normal space. Right? That means that the gradient f is actually in the normal space at x star, and then we know what the normal space is. The normal space is the space of, remember that, is the column space of this, or the row space of this. Okay. For example, if it's column space of this, means that so now I know that my gradient f at x star is in here. So it is in the normal space at x star, and that means it's in the column space of this, and that means we can find some vector such that the gradient f at x star can be written as a linear combination of the columns of this matrix. A linear combination of the columns of the matrix. Let's say the linear combination coefficient is lambda star. We can find some lambda star or negative lambda star such that this one plus, or this one equals to this times the negative lambda star. Or you move it to the left hand side, that will become this equal to 0. Okay, So that means this is in the column space of this, means that you can find some lambda star such that, which is the m-dimensional vector here, such that this sum equals to 0. Okay, so that is the core theorem in constraint optimization. It's called Lagrange Theorem. So we have just proved this theorem, and to summarize it, what it says is, if x star is a local minimizer or local maximizer, because we're looking for the first order necessary condition. Okay, so it's the first order necessary condition. So it's local minimizer or local maximizer. It could be even a local stationary point, a saddle point, as long as the derivative there is 0. But what is necessary for this x star to be a local minimizer is that it's a local minimizer of f over the constraint. This is that, let's assume, sorry, I should restate this. X star is a local minimizer or local maximizer of this function f under this constraint. And if this x star is also a regular point, meaning that at this x star, the Jacobian of H is a full row rank matrix, then there must be some lambda star, m-dimensional vector lambda star, such that the gradient of f plus the linear combination of the columns of this matrix using the lambda star as the coefficients is equal to 0. Is equal to 0. Okay, that meaning that this is true. Okay, so we're actually using this theorem. What you just need to know is that you can look at the point x star, and then you check the gradient of f and check the Jacobian of H at this point. If you can find some lambda star such that this is equal to 0, or you can find that you can see that the gradient f is in the column space of this matrix, or in the row space of the Jacobian, or in the row space of this Jacobian, then at least it satisfies the necessary condition. If it doesn't satisfy this, then you don't need to worry anymore. The x star cannot be local minimizer or local maximizer. But if it is a local minimizer or local maximizer, at least this needs to be satisfied. Although with this itself, it doesn't tell you if that point is a local minimizer or maximizer, but at least this is necessary for it to be a minimizer or maximizer. Okay, just not sufficient yet. Okay, so to dig further what we just obtained, let's say now we know that if the x star is a local minimizer of this equality constraint problem, then we know that the Lagrange theorem says that if this x star is a regular point, which you always assume, if this is a regular point, then this x star must satisfy this. On the one hand, this first one is exactly what the Lagrange theorem says. You must be able to find some lambda star so that this is equal to 0. On the other hand, since x star must be a phasor point, must satisfy this, that means h of x star must be equal to 0 as well. So these two together is called the first order necessary condition, or the Lagrange condition. Okay. All right. So in summary, what we have is, if x is a local minimizer of this equality constraint problem, and at the x star, the Jacobian of H has a full rank, then the x star must satisfy. You must be able to find some lambda stars such that x star and lambda star together satisfy this, and this here is called the first order necessary condition, or in other words, is called the Lagrange condition. Okay, and this lambda star is called a Lagrange multiplier. Okay, so this is the most important concept in constraint optimization, or in general optimization. It specifies what conditions, or what necessary conditions a local minimizer x star needs to satisfy. All right. And again, it is only necessary, not sufficient. If x star is a local minimizer, then it must satisfy this condition. But if x star satisfies the condition, it doesn't necessarily mean that x star is a local minimizer. It could be a local maximizer. It could be a saddle point. Okay. All right. Now let's look at an example. Let's consider the problem constraint, equality constraint problem here. F of x, right now the x is just a scalar. F of x is just equal to x itself. H of x is this function. Okay, we can actually look at what this function is. So let me just draw it here. Apparently, it says depends on where the x is. So it's 0, this is the 1, this is the x. When x is less than 0, it's x squared, so it's like this parabola. And then when x is between 0 and 1, is this flat area here. And when x is bigger than 1, is x minus 1 squared, so it's another parabola here. So this curve is h of x. So I want h of x equal to 0. Apparently, I just need my x to be on this interval, 0 to 1. Okay, and I'm looking for the minimizer of this function over this interval. So the function itself is like this, and then when I restrict myself to the interval 0 to 1, apparently the minimizer is here when x is equal to 0. Okay, so the x star equals 0 is the only local minimizer. Okay, and we need to check if it satisfies the Lagrange condition. But this is a special example where we actually can check that the derivative of h at a star, which is actually the Jacobian of h at x star, since just the x star right now is scalar, h is just also a scalar value function, so the Jacobian is just a single number. And this number turns out to be 0, because the derivative at x star equals to 0 is equal to 0. So this is not actually, it's not a full rank, because the rank is just 0. So in this case, x star is not a regular point, and then even the Lagrange condition is not necessary, because we don't really have a regular point here. But let's just, for sake of interest, let's see what the Lagrange condition is. The Lagrange condition says that we need the derivative of f at x star. There exists some lambda star such that the f prime of x star plus h prime of x star times lambda star equals 0. And also the h of x star is equal to 0. Apparently the second one is satisfied because x star is a feasible point, so that h of x star is equal to 0. But for the first one, we cannot make it satisfy because we know that this is equal to 0, but this one is equal to 1. The derivative of f at x star, the f is this. The derivative of f is equal to 1. So this equals to 1, this is equal to 0. So there's no way to find a lambda star so that it's equal to 0. And this doesn't mean that it violates the Lagrange condition. It's just that this point is not a regular point. We should not consider further. The Lagrange condition may not be satisfied, even if it is a local minimizer. Okay, so you know that the point being regular is also necessary when you consider the Lagrange condition. Okay, so I'll continue the discussion here. There is actually an easy way to memorize what I just said here. To memorize the Lagrange condition, the easy way to memorize it is use the Lagrange function. The Lagrange function is just look at the original problem. This, when you see a problem like this, the Lagrange function is just this function f, which is scalar valued. Sorry, that's not just generally this one. This f is a mapping. Remember that f is from Rn to R. Its h is actually Rn to Rm. Okay, and when you see this equality constraint problem, we immediately write down the Lagrange function, which is the function of x and lambda. Right now, this x is n-dimensional vector, lambda is m-dimensional vector, and this is defined to be f of x plus h of x times lambda. Okay, it's the inner product of this m-dimensional vector and this another m-dimensional vector, and this is a scalar. So altogether, it's a scalar. So this actually is a scalar. Okay, it's a scalar. So this is the Lagrange function. You just write it in this way. And then recall what the Lagrange condition is. Let's say if we take the derivative with respect to of this L with respect to x, and then take the derivative of L with respect to lambda, see what we have. We take the derivative with respect to x on this right hand side. Apparently only this one and this one depend on x. So the derivative will be just the derivative or the gradient with respect to x of L. In this case, you just think that lambda is fixed to get a gradient f at x plus the dh x. So the hx is a vector valued function. So dh is the Jacobian, right? And times lambda. Now remember that this one is n by 1. We can treat it as a column vector. This one, together with the transpose, the Jacobian itself is n by n, but with the transpose is Jacobi itself is n by n. The transpose gives us n by n. And this part is n by 1. So altogether, the gradient here is gradient with respect to x is a n-dimensional vector. And similarly, we take the derivative with respect to lambda. You can see that when we take a derivative with respect to lambda, only just this vector is left. And this vector is h of x. Okay, and this is apparently is R in Rm. Okay, so the Lagrange condition just have this equals to 0, and also this equals to 0. Right? So that's why we can always memorize the Lagrange condition as the derivative or the gradient with respect to x and lambda and set them to 0. Okay, it's just like that when we consider the unconstrained problem where we're trying to minimize f of x. Then what is the stationary point, or what is the critical point? It's just all those x such that gradient f of x equals to 0. Right now, with the constraint, you just need to introduce this Lagrange multiplier lambda such that the x star, you want x star to be a local minimizer. You just need to make sure that the gradient of L with respect to x and lambda are both equal to 0. And that is exactly the Lagrange condition. Okay, so you can memorize it as this equal to 0 and this gradient with respect to lambda is equal to 0. Okay, and this gives us as we said, this first one is in Rn, the second one is in Rm. So together they give us n plus m equations. And there are n unknowns, because it's an n-dimensional vector, there's n unknowns in here and m unknowns in here. So it's n plus m equations, and we want to solve it for n plus m unknowns. Okay, and it's not always solvable, as we know, but conceptually this should be enough. And if we can solve for that, then the points we get are candidates for the local minimizers. Just like when we solve this, we found the x such that the gradient f of x is equal to 0, then those points satisfies the point that satisfies this are candidates for our local minimizer.